Hey, what's up, everyone? Today we are focusing on multiplying two matrices together. If you recall, in our previous video, we added and subtracted two matrices together, and then we did scalar multiplication, but we never multiplied one matrix by another matrix. So that's what this video is devoted towards, and it's a little bit more complicated than you would think it is. Okay, it's not as easy as adding and subtracting with two matrices, okay? So there's a major rule that has to be followed in order for you to be able to multiply two matrices together, okay? And here it is. You can multiply two matrices if and only if the number of columns in your first matrix equals the number of rows in your second matrix, okay? So let's say we're working with matrix A and matrix B. Matrix A has dimensions of 3 by 4, and matrix B has dimensions of 4 by 2. So notice how the number of columns of matrix A is 4, and the number of rows of matrix B is also 4. The fact that those two numbers are equal means that the product of AB will be defined, okay? And then the numbers that you see in blue here, so the number of rows from matrix A and the number of columns from matrix B will come together to give you the new dimensions for your product matrix AB. So this is going to have dimensions of 3 by 2, okay? But I can't stress this enough. These two numbers are the most important, right? You have to begin by looking at columns from your first matrix and rows from your second matrix, making sure those are equal. Otherwise, the product is not defined, okay? So now let's get into an example. All right, here we have matrix K and matrix L, all right? And we'd like to find the product KL, all right? In order to do this, we first should be looking at the dimensions of K and L to make sure that this product will be defined, okay? So matrix K has dimensions 3 by 2, and matrix L has dimensions 2 by 3, okay? The fact that the number of columns in matrix K equals the number of rows in matrix L tells me that the product KL is defined. And I can now say that the dimensions of matrix KL will be 3 by 3. 3 by 3. Okay. All right. Now, that means there's 9 total elements to the product matrix, right? So I'm going to show you how to find each of those 9 elements separately. All right. And again, it's not as simple as you would think. All right. So let's say I want the first row, first column element of the product matrix. First row, first column. That means I'm going to use the first row elements of the first matrix, matrix K, and I'm going to use the first column elements of the second matrix L. And here's what I'm going to do with those numbers. I'm going to take 1 and multiply it by -3. So that's the leftmost element of the first row in matrix K multiplied with the highest element of the first column in matrix L. And then I'm going to add that with -2 multiplied by -1. Okay, so hopefully you can see where all those numbers came from. Follow order of operations. This is going to give me -3 plus 2, which results in an element of -1 for the first row, first column. Okay. All right, now I move to the first row, second column. Okay, so I'll still need the first row elements from the first matrix, but now I need the second column elements from matrix L. Okay, and here's the calculations. I'll take 1 multiplied by 2, and I'll add that with -2 multiplied by -2. So that's going to result in 2 plus 4, or 6. Okay. Now I move to the first row, third column element. I still am using the first row elements from matrix K, but now I use the third column elements from matrix L. Okay. That's going to give me 1 multiplied by 2 plus -2 multiplied by 0. So that's going to result in 2 plus 0, or 2. Right? Now notice I have used the first row elements of matrix K with all 3 columns of matrix L. So I've exhausted all possibilities with that first row. So now I'm going to be moving to the second row of matrix K. Okay, so let's say I want the second row first column element. I'm going to use second row elements from matrix K and first column elements from matrix L. That will lead me to 4 multiplied by -3 plus 3 multiplied by -1. So that's, of course, -12 minus 3, or -15. Okay, and hopefully you're seeing the pattern here. So now I want the second row, second column element. I use second row for matrix K, second column from matrix L. That'll take me to 4 multiplied by 2 plus 3 multiplied by -2. Or that's 8 minus 6, so 2. And then I move to second row, third column. Right. 4 multiplied by 2 plus 3 multiplied by 0. That results in 8 plus 0, or 8. Second column or second row elements for matrix K have been exhausted with the 3 different columns for matrix L. So now I move down to the third row for matrix K, and we'll start with the first column for matrix L. All right, so that's going to be 0 multiplied by -3 plus -1 multiplied by -1. That's 0 plus 1, or 1. Okay. Then we'll move to the second column of matrix L. All right, so that would be 0 multiplied by 2 plus -1 multiplied by -2, or 0 plus 2, which is 2. And finally, third row, third column. We're going to take 0 times 2 plus -1 times 0. It's going to give me 0 plus 0, or 0. All right, so cleaning this all up, when I'm all done, I should end up with a 3 by 3 matrix with the following elements. First row would be -1, 6, 2, then -15, 2, 8 for the second row, and for the final third row, 1, 2, 0. All right, and there you have it. All right, now we move forward. In example 2, we use the same 2 matrices, but this time I need to find the product LK. LK. All right. So we'll begin with dimensions for the 2 matrices once again. All right. So matrix K is 3 by 2. Matrix L is a 2 by 3. But now, since we're trying to find LK, I need to look at the rows from matrix, or I'm sorry, the columns from matrix L, which is 3, and the rows from matrix K, which is also 3. The fact that those are equivalent means that the product LK is defined, and it's going to have dimensions of 2 by 2. 2 by 2. All right. So there's only 4 elements to find in this particular matrix. All right. So let's go after first row, first column. All right. I will use the first row elements from the front matrix, which this time is matrix L. So I use these elements, and I use the first column matrix elements from matrix K. So that's going to lead me to the following. Take -3 times 1 plus 2 times 4 plus 0, or plus 2 times 0. So notice I'm moving from left to right in matrix L, and I'm moving from top to bottom in matrix K when I set this all up, right? So that's going to lead me to -3 plus 8 plus 0. So my first row, first column element is 5. Okay. First row, second column means keep the first row from matrix L, use the second column from matrix K. That will lead me to -3 times -2 plus 2 times 3 plus 2 times -1. Or that's 6 plus 6 minus 2, which results in 10. Okay. The first column from, or first row from matrix L has been exhausted with both columns in matrix K. So now we move to the second row of matrix L. Let's do second row from L, first column from K. So that'll lead me to -1 times 1 plus -2 times 4 plus 0 times 0. That's -1 minus 8 plus 0, or -9. All right. And lastly, we need second row from matrix L, second column from matrix K. So that'll take me to -1 times -2 plus -2 times 3 plus 0 times -1. And that is, of course, 2 minus 6 plus 0, or -4. So in the end, the product matrix LK will be a 2 by 2 matrix. The first row of that matrix is 5, 10. The second is -9, -4. Okay. Now, what I want to draw your attention to now is notice that the product matrix KL is not equivalent to the product matrix LK, which means that the commutative property does not apply to matrix multiplication. All right. Recall the commutative property of addition did work for matrix addition. We're stating now that it doesn't apply for matrix multiplication, though. Okay. All right, so now it's your turn. Click to practice one. I think it's pretty self-explanatory what you need to do. Work through that yourself. Pause the video as you do so, and then check your work with mine.